So in the last lectures we saw Fourier series, which is basically an expansion of periodic signals in terms of phasors, such that we include only the harmonics in the set of phasors that we are considering. And in this expansion we saw that we can simplify the convolution of operation if we know the coefficients in this expansion, and we also saw the conditions under which this expansion will exist. So this is true for periodic signals, where we take a fundamental frequency and its harmonics, and you express any periodic signal in terms of these phasors. But what if we are given an aperiodic signal? How do we choose the phasors? How do we compute these coefficients through this inner product or projection? So we will do this through what is known as the Fourier transform. So we saw Fourier series. Now Fourier transform is an extension of Fourier series. So we will see what is this Fourier transform now. So in order to motivate this, we will go back to our rectangular function once again. We will see from this how we can construct Fourier transform using the Fourier series itself, which we have already understood. So the rectangular function that we saw earlier, so in that, what did we do? We considered a rectangular function which existed between minus t by 4 to plus t by 4, which was 1, and after that it kept repeating for every t seconds. So this is the rectangular function that we considered, and when we computed its Fourier series, it had a Fourier series of the form sin k pi by 2 divided by k pi e power j k omega t. So this was the Fourier series expansion, and this was the Fourier series coefficients for this rectangular pulse. But one thing that we assumed in this was that the rectangular pulse in its period had 50% duty cycle. So what is this duty cycle? The duty cycle means the ratio of time for which the signal is non-zero. A rectangular signal is non-zero. So in this case, the signal is non-zero for t by 2 time. And what is the full period? The full period is t. So for 50% of the time, 0.5 is the ratio here, duty cycle ratio. For 50% of the time, this was non-zero. So this is what we refer to as duty cycle. So what if this duty cycle was, let's say, 10%? So what does 10% mean? So in that case, then we'll have a very narrow pulse, something like this, right? So this is minus t by 2 to plus t by 2. But in this case here, we will have minus t by 20 to plus t by 20. So then the duration for which this is non-zero is t by 10. The total period is t, so we get 1 by 10. So this is 10% duty cycle. So as you reduce the value of d here, that is the duty cycle ratio, then the signal becomes narrower and narrower. So if you make it, let's say, 80%, so what happens? Then the signal widens, or the duration for which it is non-zero, it widens, something like this. So you can change the duration for which this is 0 versus non-zero by changing this duty cycle. Now what if we alter this duty cycle? What happens to the spectrum? What happens to the Fourier series coefficients? Now if you compute that, that is not very difficult to compute. So what changes is the computation of the Fourier series coefficient. We had 1 by t integral minus t by 2 to plus t by 2 set of t e power minus j k omega t dt, right? So the only thing that changes here is the limit. The limit for which this is now non-zero is given by minus dt divided by 2 to plus dt divided by 2. So if d was 0.5, then you get minus t by 4 to plus t by 4. If d was 0.1, then you get t by 20 at the top and minus t by 20 at the bottom. That's the only thing that changes, nothing else changes, right? So what is this? This is 1 by t e power minus j k omega t by minus j k omega t by 2 minus dt by 2, right? So this is 2 pi divided by t. So the denominator k pi still remains as such. The only thing that now we have it changes the numerator, which is sine k. So for omega we substitute 2 pi by t and dt by 2 from the limits. So that gets cancelled, and what we have is k by t. So this is what we have as the coefficients. So now the entire Fourier series expansion becomes this for a rectangular wave with a duty cycle given by this ratio d. Alright. So what does this tell us? So if you look at this, what is A0? We'll once again do the same thing. What is A0? When A equals to 0, we get sine k pi by d divided by k pi by d into d. So A naught is actually equal to d, which makes sense because A naught represents the amount of DC component that is present in one period. So as the duty cycle increases, the DC component increases. It remains flat for a longer time. So this changes depending upon what is the duty cycle. What is A1? So earlier we had A1 to be equal to 1 by pi for k is equal to 1 for duty cycle half. Now in this case we have sine pi d divided by sin pi. Okay, so this is A1, and A2 equals sine 2 pi d divided by 2 pi. So earlier we had A2 equal to 0, that is when d is equal to 0.5, A2 was 0. But in this case, this need not be equal to 0 all the time. So let's say d was 0.1. Then the numerator becomes sine 0.2 pi, which is not equal to 0. So whatever was a function which looked like this will now start becoming something like this, right? So A3, once again we have sine. So if t was 0.1, then we have here 0.1 times pi, here once again 0.1 times 2 pi, and here 3 pi times 0. None of these would be 0, right? So you will have a lot of values here which are non-zero. Earlier we got 1 by pi, 0, minus 1 by 3 pi. So let's plot this and see. So let us say we plot this for d is equal to 0.1. So if we plot for d is equal to 0.1, then at 0 we had 0.1. So a naught is equal to d, so we will have 0.1, and then a1 is another non-zero term, and a2 is another non-zero term, a2, a3 is another non-zero term, a4 is all, they are all non-zero and they are all positive because they have not crossed that line, right? So they cross the line only when they attain 0 at some point. So they remain non-zero for a long time. But let's say what if we plot d equal to 0.5 on top of this. For d is equal to 0.5, a naught is 0.5, a1 is some 1 by pi, a2 is 0, a3 is minus 1 by 3 pi. So as you can see here, the signal looks like this. For the envelope of the signal at least looks like this for a larger duty cycle, and the envelope of the signal looks like this for a smaller duty cycle. So it's the same shape, but for a smaller duty cycle it looks as if it was stretched in frequency. Okay, so that's how this expression turns out to be. We can view this in a different manner. What if we retain the period for which the signal is non-zero, but then just change the period of the signal? In other words, what if we transform this signal by just changing its period? So what if I come up with a rectangular function which looks like this? So what have we done here? So this is 1, from minus t by 4 to plus t by 4. But it continues to be 0 for a longer time. Let's say this is some minus nt and this is some plus nt, where n, for example, n could be some 10. So what have we done here? So we have essentially took the same rectangular wave, but then increased the period and kept the duration for which it is non-zero to be the same. So if you compute the duty cycle of this signal, the duty cycle is very, very small. So what is the duty cycle here? The duration for which this is non-zero is t by 2. The entire duration is now 10t, or in this case 20t. Right. So the duty cycle is basically now 1 by 40. So which is very, very small. So the duty cycle has changed and the fundamental frequency has also changed. Now what is the fundamental frequency? It is 2 pi by 20t, which is pi by 10t. Earlier it was 2 pi by t. So the fundamental frequency has now decreased. Earlier it was just 2 pi by t. 2 pi by t is much bigger compared to 2 pi by 20t. Right, it is 20 times now smaller. So the fundamental frequency has increased. So the frequency component, so earlier k omega when k is equal to 1, k omega corresponded to 2 pi by t. Now for this period k equal to 1, k omega would correspond to 2 pi by 20t. In other words, let's say if this was the spectrum that was plotted for omega equals 2 pi by t, this would be the spectrum that you would get for omega is equal to 2 pi by 20t. Why? Because when k is equal to 1, it would correspond to 2 pi by t, and when k is equal to 1 here, it will correspond to much smaller omega. So it has to up, so 2 pi by 20t will come before 2 pi by t. So the number of frequency components that we have in the spectrum will increase. So the resolution of the spectrum increases. Okay. So the smallest frequency that we were able to resolve in the case of omega equal to 2 pi by t was 2 pi by t itself. But the smallest frequency now has decreased to 2 pi by 20t when you increase this period. So as the period increases, the resolution increases. Okay. So we have more and more values of this coefficients becoming non-zero and appearing here. So the density of the frequency components increases. So basically what happens, more frequency components, more harmonics keep adding up together. It's the same rectangular wave. All we did was to increase t. Okay. So we just change the period. We keep increasing the period while we keep the duration for which the signal is non-zero to be fixed. So the duty cycle reduces. Okay. So you keep increasing the time duration of the signal's period. So what are we doing here essentially is keep increasing the length of one cycle. So that's what we say by saying the period increases while keeping the non-zero duration of the signal to be the same. So that's what we refer to as the duty cycle going down. So the duty cycle goes down and the period increases, which essentially means that the non-zero duration remains the same, but the signal period keeps increasing. In the corresponding Fourier series coefficients, if you plot them as a graph, then the number of points keep increasing. That is the number of harmonics that you have to add to represent this new signal keeps increasing. So the frequency components keeps adding up, which means more and more frequency components add, and then the density of the plot changes. It becomes more and more dense. So what if we let t tend to infinity, right? If we let t tend to infinity, we will just end up with only one cycle. So we would have effectively constructed an aperiodic signal. Okay, so if we let t tends to infinity, then this n here goes to infinity. If this n goes to infinity here, then effectively what we have is just the rectangular signal. So how do you think in that case this plot will look like? So by the same intuition that we have gotten so far, this should become more and more dense, and this should almost become like a continuous plot, right? So that is what we would refer to as Fourier transform. We will see more clearly this now. So we have some signal z of t. Let us assume that it is periodic for now. So if it is periodic, then we will say that we can represent that using Fourier series representation, and this is a Fourier series representation. Now what is AK in this Fourier series representation? How do you compute this AK? You compute this AK by projecting it onto the original signal. So that projection we get is z of t power minus jk omega t dt, right? So that is what we have here, and this is integral over one period. So this is the Fourier series representation of a periodic signal with period capital T. Now what if we assume that this t tends to infinity? So that is what we are going to do now. Whatever discussion that we had earlier, we are just formalizing this mathematically. So if we let t tends to infinity, then first thing we are going to do is we are going to write 1 by t as, we know that t is 2 pi by omega, so which means we can write omega equals 2 pi by t, right? Or in other words, we can write 1 by t as omega by 2 pi. So we will just replace 1 by t with omega by 2 pi, okay? And then we will call this entire integral as some z of jk omega. It is not a function of t because you are integrating out t. The only thing it is a function of is jk omega. Everything else gets integrated out. So we will just simply call this entire integral by one variable, and that variable is what we will call as z of jk omega, okay? So earlier what did we say? We said that AK was equal to, in this case, omega by 2 pi z of jk omega was a Fourier series coefficient, AK, okay? We are just now, that's just splitting that into two parts. We will see why we are doing it, into omega by 2 pi and zjk omega. We are doing this because we are now going to let t tend to infinity, right? So because of that, we just cannot keep 1 by t here, you will get 1 by infinity form. So we want to do some manipulation to get rid of that. So we are separating that out, and then we are writing omega by 2 pi and z of jk omega. Alright. So now if t is tending to infinity, what happens to 2 pi by t, which is omega? That will tend to a very, very small number, like it will tend to 0, okay? And you can say that as t tends to infinity, 1 by t will tend to 0, which means this is a very, very small number. So let us denote that by some epsilon. This actually goes to 0. So applying limit to this summation, what happens to omega now? So now omega is a very, very small number. That is, it is epsilon by 2 pi z of jk epsilon e power jk epsilon t, and there is this summation. Now this summation k runs from minus infinity to plus infinity. If epsilon is very, very, very small, then k times epsilon can possibly cover every region in this in this line from minus infinity to plus infinity. So any point that you can consider here, any point that you can think of, can be written as k epsilon, as long as epsilon is very, 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 very small. So because of this reason, what you can do is you can replace this summation with an integral, because now, because epsilon is arbitrarily close to 0, you can think of this entire summation which is running over k epsilon with k from minus infinity to plus infinity. K epsilon can be any arbitrary omega, any omega that you can think of in this entire line from minus infinity to plus infinity. It can take any value continuously, because now it becomes like a continuous number. Earlier it was a discrete number. For k is equal to 1, you got number, k equal to 2, you got another number. So it was discrete. But now because this epsilon is arbitrarily small, now you can think of this as a continuous number. So once you have a continuous number, you replace this summation with this integral, and it runs from minus infinity to infinity. You just replace this k omega with another omega, or let's probably make life little easier to follow. So let's replace k omega with nu. Okay, let's call this as nu. Okay, so we'll say omega is very, very small. So we'll replace omega with k epsilon. Now k epsilon is a continuous number, so we'll replace that with some nu. We'll say that this is continuous. Okay, so now wherever there is k omega, you replace that with a continuous variable nu. Now we have omega here. So what is omega? Omega is epsilon, which is a very small value of omega, is as good as saying it is d nu, right? So what is nu here? Nu is any number between minus infinity to plus infinity that can be denoted by k epsilon. But what is the smallest that you can denote? That is epsilon. In other words, that is d nu, right? So that is what we have. So the same equation, if you just simply let t tend to infinity and apply the limits, this equation exactly becomes this equation. All we did here was just rename variables so that we will get rid of the problem of infinity. Okay, so we got to a continuous set of frequencies from discrete set of frequencies in Fourier series. So in Fourier series, what happens? We had discrete set of frequencies, and as you increase the time period, the density kept on changing. We had more and more frequency components. So when the period goes to almost infinity, the signal is aperiodic. The density here also becomes so high that it now starts looking like a continuous set of numbers instead of discrete set of numbers, and that's what we are observing here. Now because it becomes a continuous set of numbers, we have a continuous number here, and the summation now changes to an integral, and this omega, which was a very small number, becomes d omega or d nu here. Okay, so this is now our Fourier representation. Earlier we had Fourier series. Now the period kept on increasing and became almost infinity, which effectively gave us an aperiodic signal, and the frequency components keep on adding up. So we had a very dense representation of the frequencies, or a very dense amount of harmonics being added up. Now we ended up getting a continuous set of frequencies from that, from discrete set, and we got this representation. So this is equal to z of t for aperiodic signals. Okay, all right. Now how do we compute this coefficient now? Remember, this is the Fourier series coefficient that we had, the Fourier coefficient that we had here. So all we were saying here is, we said that z of t is equal to ak e power j k omega t summation over all k's. So we have just simply said, earlier we can represent any signal as sum of phasors. Now we are saying that okay, it is sum of phasors, this is still sum of phasors, but now the phasors are so dense, they are so continuous that we cannot simply sum them up, we have to integrate them. So that is all we are still saying. This still means that you can represent any signal using just phasors, which are orthogonal bounded basis functions. Now these phasors that are required are not discrete anymore. You require a lot of them. You require a very dense set of phasors that you now represent the summation using an integral because they are so dense. Okay, so this is the representation for the aperiodic signal in the Fourier basis, or using the phasors. Now how do we compute these Fourier coefficients? Now we did the same thing earlier, right? So all we did was, the computation of ak was exactly this. You just find the inner product of z with the phasor in one period, but this period now tends to infinity. That's all. So all we do is same thing. So we'll just let t tends to infinity. Now this is how you compute your inner product. Because earlier we had the problem, we had to divide by 1 by t, or we had to divide by the energy of the basis function, and that's where we had a problem that it might go to infinity. But then we got rid of that problem here because this is where the normalization comes into picture. And then we got rid of that by changing this 1 by t to omega by 2 pi, and this omega just brought in inside this integral help us to convert this entire summation to an integration. So the final thing that we had here was only the inner product without the normalization. So this coefficient now represents the inner product without the normalization, and we can compute the inner product. There is no issue with that. Alright. So now we have a new Fourier representation. Earlier we had a Fourier representation for periodic signals that gave us a discrete set of frequencies with which we can represent only the harmonics of the fundamental frequency. Now if there is an aperiodic signal, there is no periodicity, there is no fundamental frequency, so we cannot use those concepts, but we can use those ideas to say that the fundamental frequency now is almost going to 0 because the fundamental period is almost infinity, and by applying the limits we got a new representation, and that representation is the Fourier Transform representation. So in this representation what we have is that you can say the same thing, that is any aperiodic signal can be expressed using phasors, but you will require a dense set of phasors that you cannot simply add them, you will have to now integrate them, and you can use the same notion of inner product, just simple projection without normalization, because normalization is taken into account and you get this 1 by 2 pi here. So all you have to do to compute the coefficient is simply the projection, that is it.